Good morning, all of you. If screen is clear to you and if I'm audible, please say yes in the comment box. If everything is fine. If voice is okay and if screen is fine, then please say okay. Then we shall start. Good morning, all of you. Good morning, Lokesh, Usha, all of you, Kalyani and all. Okay, yeah. I hope everything is going fine. So if we continue from yesterday's class, basically before the closure of yesterday's class, we are looking at the concepts of integration, correct? And we have discussed a few standard improper integrals, which is gamma function and beta function. Then we have seen how definite integrals are connected to these gamma and beta functions as well, correct? And also in yesterday's class, by the end of the class, I gave you a initial idea of what we are going to deal in today's class. Basically, we are going to deal length of curves, means the geometrical aspects of integration again. And if time permits, we'll also visit some partial differentiation techniques and we'll introduce a two-variable calculus in today's class. Okay, and before starting today's class, I would like to give you timings for tomorrow. Tomorrow we'll be having 4 hours class in 2 sessions, basically 2 hours and 2 hours. First session is from 7:45 to 9:45 and second session is from 10:30 to 12:30. Okay, and I hope by tomorrow we'll end up this basic calculus as well. Okay, so please don't miss all these 3 sessions. So please look here. We'll continue. So as I told you, we'll be starting our concept with the length of a curve. Length of a curve means basically if there is a curve of some not known geometry to you, then you need some differentiation technique to measure the length of the curve. So we'll try to deduce a formula to find the length of a curve. Okay, normally physically without mathematics, if you want to do, suppose if this is the curve that you want to measure the length, suppose if these are 2 points, then take a thread, put one end at this end and try to arrange this thread along this curve. Then take the 2 ends, stretch it and put it on a scale, then you'll be getting what's the length of this curve. This is how physically you measure the length of this curve. But to find it mathematically, let us see what happens. Okay, let y is equal to f of x is a curve which is continuous. We can write which is differentiable directly, because if a function is differentiable, that means we will be having the function to be continuous. Differentiable in x belongs to a comma b, then you can put an open here so that no issues. X belongs to a comma b, then the length of the curve, let me shorten this a bit so we can write the formula also here. Okay, yeah, then the length of the curve y is equal to f of x between x is equal to a and x is equal to b is given by now let us see what's the formula for this. Okay, so for that let me try to write something here. 0 x y, basically this is origin O, 0 comma 0 points here. So see here, now let us suppose this is the curve y is equal to f of x. Okay, so if this is the curve y is equal to f of x, now to find the total length of this curve, let me consider a small region dl here. Okay, where dl is a small length of that curve, a differential length basically. Now let me resolve this dl into a small triangle which is dx, whose sides are dx and dy. Means if I enlarge the things, I'll be having something like dl, then we have dx and then we have dy. So basically this length dl I am resolving into x component and y component. Okay, so in that case, if you see, when this dl is very small, let me show you something. If this dl is very small, then this straight line joining these 2 points AB, if I call these points as AB, then if you see this straight line joining AB and this curve are almost same. Basically, if you see a circle, if you consider very small length, this curvature effects are neglected, correct? So within this small length, this curve which is connecting these points A and B can be replaced by a small straight line AB. Okay, segment AB. So from this triangle, you know, this is a right angle triangle now, because you know x and y coordinates are perpendicular to each other, which means the segments dx and dy are also perpendicular to each other. So now if you apply Pythagoras theorem for this particular triangle, we have from Pythagoras theorem, dl square, which is basically the hypotenuse in the triangle, is equal to dx whole square plus dy whole square. Is it the case? So from this triangle we can write this expression. So with this expression I'm continuing in the next slide. So please see here. This implies dl whole square is equal to dx whole square plus dy whole square, which implies dl whole square is equal to, if I take dx square common, dx whole square, if I take it common, I'll be having 1 plus dy by dx whole square. Yes or no? Because this dx square, when it comes here, it can be written as dy by dx whole square, and this implies dl is equal to, means basically if you take square root, you will be having dx into square root of 1 plus dy by dx whole square. Okay, this is what you have as an expression to evaluate the small strip length of this curve f of x. So this can be written as dl is equal to square root of 1 plus dy by dx whole square into dx. So basically this is expression to find the infinitesimally small length of a strip. So if you want the total length of the curve, now you need to integrate this expression between the points of interest. Here our points of interest are basically x is equal to a to x is equal to b. Means basically if you see, it could be something like this, x is equal to a and this is x is equal to b. So if you want the total length of the curve in between the 2 points, therefore total length of the curve, y is equal to f of x between the lines x is equal to a and x is equal to b is L is equal to c. Now this is dl, so if I want L, I need to integrate between a to b. So if I integrate between a to b, we'll be having root of 1 plus dy by dx whole square into dx. So this is the expression for finding length of the curve, and this question was asked 3 times in GATE and 2 times in ESE exam. Okay, in ESE scientist exam. So please be careful of this particular formulation, and this is how you achieve it. And now since you have any y as any function of x, then you will be getting this dy by dx as a function of x. So if you substitute here, then you know with our standard integration procedures, we'll proceed the integration and then apply these limits a to b. You'll be getting a numerical value. And now we'll be looking at one question and to analyze this particular expression. Meanwhile, you can take these notes. Okay. So it's just of the minimum basic that whenever your length is very small, the curvature effect doesn't get valid. So I mean, it can be approximated as a straight line basically. So the line joining these 2 points is same as almost the curve that's connecting these 2 points. The length of this green line and yellow line will be almost the same. Okay. See, some of you told me that you are facing difficulty with finding notes of class. If you click that link, it's showing you invalid. But to get the notes from that link, you should have Telegram app installed in your mobile or in your PC. Okay. So please do that before clicking that link, because it's basically a link that connects you to Telegram app. So if you don't have Telegram, you'll be facing difficulty over there. Okay. Okay. So fine. We achieved this formula. Integral a to b root of 1 plus. Good morning, Hema. So see here, integral a to b root of 1 plus dy by dx whole square into dx is the appropriate formula for this. Okay. So now with the knowledge of this, I would like to discuss a question that came in ESE in 2018 April. So see here, the question was asked something like this: the length of the curve y is equal to 2 by 3 into x power 3 by 2. 2 by 3 into x power 3 by 2 between the points x is equal to 0 and x is equal to 1. between the points x is equal to 0 and x is equal to 1. Okay, so now you need to find the length of this curve, and if you see, you don't know how this curve x power 3 by 2 looks like in general, okay? So this question was asked in ESE, and trust me, in ESE you can't use calculator, okay? So you need to get the answer of this question without using calculator and tell me the value. You can round off to 2 decimals as well. I would like to give some time for you, so please take this. I'm waiting for your answers, so please try to apply this expression, and you know the limits of integration from 0 to 1, so you can get the answer for this. And you have y is equal to f of x, 1.22. Good here, it's a correct answer. Still, anyone could get that answer, 1.22. But the important thing is you should tell this without using calculator, okay? So please make a note of that, 1.2. Neerja, it's correct. So see here, I'll be solving this question since some 2-3 are getting the correct answers here. Solution. Now how to solve this? Yeah, 1.22. All of you are correct, Vikas, Rahul and all. So see here, what is y? Y is equal to 2 by 3 into something happening. Okay, x power 3 by 2. So what is dy by dx from here? This implies dy by dx is equal to, let me write this 2, it got repeated 2 times. Okay, so is equal to 2 by 3 into, differentiation of a polynomial function is n into x power n minus 1, which is basically 3 by 2 minus 1, correct? So this 3 gets cancelled, 2 gets cancelled, and 3 by 2 minus 1 is nothing but 1 by 2. So dy by dx is equal to root x. This is what you have, correct? So let us retain this expression. Now, what's the length of the curve? What's the definition that we have for length of, or what's the formulation that we have for length of the curve? L is equal to integral a to b, and if you see here, the limits of integration are from 0 to 1, root of 1 plus dy by dx whole square dx, and dy by dx is basically root x, so dy by dx whole square is x dx, correct? So now you need to integrate this expression and evaluate this value. So if you see integral 0 to 1, this is 1 plus x whole power 1 by 2 dx. So if you integrate this 1 plus x whole power 1 by 2, you will be having 2 by 3 into 1 plus x whole power 3 by 2 within the limits 0 to 1, correct? Because the integration of a plus bx whole power 1 n is nothing but a plus bx whole power n plus 1 divided by b and all these things. So see here, this is equal to 2 by 3 into, now if you substitute the limits 1.218, it's correct, Nagsai, see here, if you substitute 1, you will be having 2 power 3 by 2 minus, if you substitute 0, there is 1 power 3 by 2, and the value of 1 power 3 by 2 is 1 itself, correct? So if you perform this calculation in examination, 2 by 3 into this 2 power 3 by 2 can be written as 2 into root 2, correct? Minus 1. So 2 by 3 into, root 2 value is 1.414. So 1.414 into 2 is 2.828, and 2.828 minus 1 is 1.828. So if you cancel this, 0.6, then 0, then 9, because 3 9s are 27 and all. So if you multiply this 2 into 0.609, 2 9s are 18, 2 6s are 12. So 1.218 is the correct answer. So if you round off it to 2 decimals, you'll be getting 1.22. Okay, so which is approximated as 1.22. So this is how you'll find the length of this curve. It's basically, if you know this formulation, then this is just a 2 steps simplification beyond that. Okay, so this question has been asked in GATE exam and as well as in ESE exam. Okay, so this is how they'll give you some curves which are of not definite geometry, which is known to you. Then you need to apply this particular analysis and you need to get the length of this curve. Okay, so now moving ahead in this lecture, I would like to give you one particular thing or one particular concept of integration, finding lateral surface area of solids. Lateral surface area of solids. Lateral surface area of solids. Now see here carefully. X-axis, x, 0, y, minus 1. Okay, now let us suppose there is some curve like this, some random curve, y is equal to f of x. Okay. Now see carefully, if I rotate this curve about this x-axis, yeah, okay, so see here, let us suppose my hand is x-axis and this pen is a curve. So if I revolve this curve around this x-axis, then this curve which I am rotating will form a solid curve. For example, if I am rotating a straight line about my hand, you will be getting a cylinder, yes or no? And if I rotate the inclined line about my hand, you will be getting a cone, something like this, correct? Basically, if you revolve a curve around any axis, you will be getting some solid generated, correct? So if this is the case, then definitely the solid that gets formed will have some surface area, some volume and all. So now let us try to see how we can evaluate them using this integration, okay? And questions came from this aspect also in GATE, okay? So please stay tuned. If y is equal to f of x is the curve, then how do you define lateral surface area? See here. If f of x is differentiable in x belongs to a comma b, means basically if you consider this point as x is equal to a and if this point as x is equal to b, then see here, if these are the 2 points, then if you revolve this curve around this x-axis, definitely some solid gets generated. Now let us try to see the formulation for that. Between x is equal to a to b, then the surface area, in bracket you can put lateral. Lateral is which is the surface area of the curved part basically. So the surface area of the solid generated, of the solid that is generated by revolving the curve y is equal to f of x around about, you can say, evolving the curve about x-axis. About x-axis is given by a is equal to, now we'll see what is this formula, okay? So we'll see basically what's the formula of integration for getting the lateral surface area of the solid. Now for that I want you to understand something. See here, let us suppose this is dl again, okay, where dl is small length of the curve. Now when this complete curve is getting evolved about x-axis, means see, basically when this complete curve is getting evolved about x-axis, you will be getting a solid. So out of this complete curve length, I am taking a small length dl, so that if I evolve this length dl, then I will be getting some disk, correct? Which means if I evolve this dl portion around this x-axis, I will be getting some curve which is like this, okay? Some portion like this, some disk basically, correct? Where your x-axis is passing like this, or is in somewhere here, and this length is dl. So if you want to see the things clearly, you can hatch this part maybe. Okay, so you will be having some disk of thickness dl, and see carefully, if this is y is equal to f of x, at this point this is y, correct? Which means this height that we are concerned is y, yes or no? So which means if you rotate this dl around this x-axis, so basically if you rotate this cap around my hand like this, then you will be getting a small disk of thickness dl, and this height is y, because here this function is y is equal to f of x, and at corresponding value of dl will have this y as the value. So see carefully, when this is very small, can I write the surface area of this disk, because basically this is a circle and this is of thickness dl, so can I write the area dA, means basically the lateral surface area formed by revolving this strip dl. Can we write that dA as dA is equal to, see, this is a small disk, and if I want to know the lateral surface area of this, basically if you see, let me show you what is a lateral surface area here. Okay, so see here, when I am evolving this portion like this, I'll be having this lateral surface area that is getting generated. Okay, basically in the beginning I wanted you to show the volume so that it's forming a disk. Now I wanted to show you the lateral surface area, of course on the back side as well. So if I want to write expression for this dA, this is dl, then this is y as of our discussion earlier. Similarly, this height is also y. So this is a disk. Can we write 2 pi y, where y is basically the radius of the disk? So 2 pi y will give me the circumference of this disk into this portion dl. Yes or no? Can we write this expression for dA or not? Please tell me. Can we write? Because 2 pi y is the radius, 2 pi y is the circumference of this disk, and since dl is the thickness, by multiplying these two, can I get the surface area of this particular disk? Yes or no? Please say yes if you understand this. Okay, Vikas, fine. All of you, I want all of you to respond. Did you understand why we are writing this formula for dA? All of you? Okay, fine. Many of you are saying yes, so I'm happy for that. So now from this expression, I'm integrating this. Okay, see here. Krishna, I'll come in, so no issues. dA is equal to 2 pi y into dl. This is what we have. Correct? So if you want to integrate this expression, we have y is equal to f of x. So this implies dA is equal to 2 pi y into, and if you see here, this dl, we have seen what's the expression for dl of a curve. The expression for dl of a curve is 1 by dy by dx whole square into dx. This is what the expression we have for dl, correct? We have seen in our previous session, just minutes ahead. So dA means the small differential area that we get is equal to 2 pi y into square root of 1 plus dy by dx whole square into dx. So if you know that y is equal to f of x, and if you want to see what's the volume of solid when it is rotated between the lines x is equal to a and x is equal to b, then you can go for integration from x is equal to a to x is equal to b, and this also gets integrated from x is equal to a to x is equal to b. Now you have this y in terms of f of x. Basically your function is defined, so y is equal to f of x is known, which means you can substitute this y in terms of x, and when you know y in terms of f of x, similarly this dy by dx is also known to you, so you will be getting the answer if you integrate. Okay, so now we can write this formula there. A is equal to integral a to b 2 pi y into, let me write this expression a bit for dA is equal to 2 pi y dl. Okay, so 2 pi y into square root of 1 plus dy by dx whole square into dx. Okay, so this is basically the area or the lateral surface area that gets generated when you evolve a solid around this. Okay, so you will be forming a disk when you rotate this small dl. So this is the formulation for surface area of this. So when you integrate this from a to b, you will be getting the total lateral surface area of the solid. Okay, is it clear? Is this things clear here? So this is how you will generally integrate, and this question is also came in GATE many times. Okay, a lot of times this question was even asked in exams, and actually this is of much use to mechanical and civil engineering students, because in mechanical and civil you will be generally dealing with solids, and you need to find things like surface areas and volumes and all these things. Okay, so now let me tell you one thing. With the help of this knowledge, if I ask you lateral surface area of cone, since this is known to you since you are schooling, I want you to look at this. Lateral surface area of cone means basically if there is a cone like this, where this is the axis, if there is a cone which is looking something like this, and if this radius of the cone is r, and if this height of the cone is h, if a function f of x is evolving about y-axis, simple 2 pi x into root of 1 plus dx by dy whole square dy. Okay, limits of integration of a y limits, y1 to y2. Okay. Yeah, we Manoj Kumar, sir, x is equal to a and x is equal to b because length. Yes, because we want to consider the length between x is equal to a and x is equal to b. If this gets extended, this limit also gets extended. Okay. So see here, if this is the case of a cone where this radius is r and this h, this height of the cone is h, then what could be the surface area, lateral surface area of cone? You might have studied in your schooling. So tell me this answer. I hope all the doubts are clear so far. So please tell what's the lateral surface area of cone. If you remember something, probably in 8th class mensuration and all, you could write this, and many of you might have been using this still. So if this is a cone whose vertical height is h and if base radius is r, 1/3 pi r square h. Suma, I am not asking the volume of the cone, I am asking the lateral surface area of the cone. Okay. Pi r h by 3, no. Pi r into h plus r, pi r l. Lokesh, you are correct. Annapurna, you are also correct. Answer is pi r l. Pi, let me write capital letters because I represented in capitals. So pi r l, where l is slant height of the cone, which is given by r square plus h square. Correct. This is what you have seen for lateral surface area of cone in your schooling. Correct. And so since we developed theory, now to get this formulation, let us see whether we are getting this formula or not using this particular knowledge that we attained. Okay. So since I gave you some expression for finding lateral surface area, let us see whether we are getting this formula or not. Okay. So whoever don't know this, no issues. You can take privilege of this for the time being. So see here. I hope things are clear. Okay. So see. Let us suppose 0, x, y and minus y. Okay. Now let me take a line y is equal to mx, which is passing through origin. Okay, y is equal to mx. Now if I revolve this line about this x-axis, can I get a cone? Yes or no? If I revolve this line about x-axis, definitely I can get a cone like this. Okay? Because if I revolve this line, it happens. So now if you want to find this lateral surface area, now you know the equation of the curve y is equal to mx. Let us substitute here. And one good thing about this particular question is this m is a constant, because normally if you take this curve here, y is equal to f of x and dy by dx, slope of this line is not a constant. But here in this case, this line is a constant. Slope of this line is a constant, which means the value of this m is fixed. Okay? Once you define the straight line. So now if you apply this formulation, let us suppose I am considering till the length r. Okay, let me write dimensions with some other color so you can see. Let us suppose we are writing this as h, because we mentioned that the height of the cone is h and this length is r, which is base radius of the cone. Then what could be this point? H comma r. Correct? Because h is the x coordinate and r is the y coordinate. Now if this point is h comma 0, this length of the cone is h. Correct? Is it okay so far with the dimensions? I want to discuss the cone which is having a height of h and base radius as r. So that's why I have drawn this curve. Is it clear so far? Any issues till now? Okay. So it's clear. So now let us apply this formula. Integral, I want the area of the curve, lateral surface area of the solid, when this curve y is equal to mx gets revolved, and my length of integration is from 0 to h. So 0 to h dA, basically the lateral surface area, is equal to 0 to h 2 pi y, and you know the equation of this curve is y is equal to mx into square root of 1 plus dy by dx whole square, and dy by dx is nothing but slope. For this curve, this m is the slope, so m square into dx. Correct? So this is the expression or integration that we need to work out. So see here, if you work out that integration, a is equal to, basically I am applying the integration, so integral 0 to h, okay, integral 0 to h, then 2 pi mx into square root of 1 plus m square dx. Correct? So this implies a is equal to, now if you see one thing, this m is a constant, which means this root of 1 plus m square is also a constant, and this 2 pi m is also a constant. So I am bringing all the constants out of integration. So 2 pi m into square root of 1 plus m square into integral 0 to h x into dx. This is what we have. Correct? So now see carefully. A is equal to 2 pi into, now what's the value of m? See here. If this line has slope m and if this is theta, then this m is same as tan theta, which we discussed in second lecture when we are dealing differentiation, physical significance of differentiation. Correct? So m is equal to tan theta, and from this triangle, if this side is h and if this side is if this side is h and if this side is r, then what's the tan theta from this triangle? Tan theta value is equal to r by h. So m value is r by h. So let us see here. If m value is r by h, let me substitute the things. R by h into root of 1 plus r by h whole square into integration of x is x square by 2. So within the limits h to 0 to h, we will be having that as h square by 2. So let us simplify these things now. A is equal to, first of all, this 2 and 2 gets cancelled. Then pi into r by h into, if you take LCM, you will be having, this is r square by h square. So r square plus h square divided by r square into h square. Sorry, this is h square, correct? So now, if you simplify the things, h and the square gets cancelled. And if you see, there is h square under root, which means with the remaining h, I can cancel this h square as well. So which means for lateral surface area, I have the formula pi r into root of r square plus h square, which some of you told correctly during the beginning of this discussion. Okay, so this is how you will find the lateral surface area of solids, basically using this particular integration analysis. Okay, so this is the lateral surface area of the cone, which is having a base total height as h and base radius as r, and slant is root of r square plus h square from Pythagorean theorem. Okay, so please take this. Then we'll go for how to find volume of solids. I think I'm blocking the things, so you can take now. Clear so far? Like this, if they give any f of x in exam, you could apply these things and you can integrate simply, as long as you remember this formulation. Okay, clear so far? Any issues? Can I continue? Can we move ahead? All of you, please respond. Okay. Okay. So I think all of you are getting the things now. So then we'll go for something called volume of solids. Okay. So we have seen how does the lateral surface areas be evaluated using this integration techniques. Now we'll go a step ahead and we'll see how the volumes are calculated using this. Okay. Volume of a solid. Volume of a solid. Again, see the same things I'm going to draw once again here. The same diagram. Origin x, y, and minus x. Then suppose if this is the curve, y is equal to f of x, and if this is the line, x is equal to a, and if this is the line, x is equal to b. Okay. x is equal to a. Okay, x is equal to b. Again, now if you consider a small length dl, and if you rotate this dl, I mean if you evolve this dl about this x-axis, then again you will be getting a disk which looks something like this. dl something like this, some disk like this, where this is x-axis with origin being somewhere here. So basically you'll be getting a disk like this again. Okay? So now if you want to know the volume of this disk, which is basically the volume bounded by this tape, see here. So before going further, let us write some TI that's of interest to us. Let y is equal to f of x is a function differentiable in x belongs to a comma b, differentiable in x belongs to a comma b, then the volume of solid that is generated by revolving the curve y is equal to f of x between the lines x is equal to a and x is equal to b is given by v is equal to, now let us see the formula, what v tells us. Now see, you all understood why the surface area, lateral surface area of this strip is 2 pi y into dl, correct? Now if I want to talk about volume dv of this part, what could be the volume of this part if this radius of this circle is y, where basically this height is y? Please tell me what could be the formula for dv. This is a circle of pi y square and the thickness of this disk is dl. Pi r square is the area of this circle, which is pi y square. What's the total volume of this small disk? Pi y square dl, correct? Rahul, you're correct. So x-axis minus y, and yeah, sorry, this is minus y. Thank you. Okay, so no issues. Pi y square dl, correct? Because pi r square dl, because basically I have indicated this r as y, this is pi y square dl, correct? So pi y square into dl, where pi y square is the area of the circle. See, basically if you are having a small disk like this, then if you want to find the volume of this, you should know what's the radius of this, correct? If this radius is y, then pi y square is the area of this into this height h is the multiplication for finding the volume of this small disk. That's what the scene we have here. But of course, this is in vertical state here. So pi y square into dl. Okay. Pi y square dl. So this is the expression that we got for finding small volume of this part. So if dv is equal to pi y square dl, let us see what's the expression for total volume. dv is equal to pi y square dl. So this implies dv is equal to pi y square into, in case of dl, we can write 1 plus dy by dx whole square into dx, correct? Because for dl, this is the expression that we attained. So now if you want complete volume, this should be integrated from x is equal to a to x is equal to b, pi y square into square root of 1 plus dy by dx whole square into dx, correct? So this is the formulation for volume of a solid that gets generated when you evolve a curve y is equal to f of x about x-axis. Okay, so you should write this formula here. Integral x is equal to a to x is equal to b, pi y square into root of 1 plus dy by dx whole square into dx. Okay, so basically this is the formulation that you use in generating or in finding the volume of the solids that get generated. Clear so far? So please take this. Is it okay to all of you? Why did I write this small volume dv as pi y square dl? Then I'm applying this integration. Okay, Vikas, all of you who are on live, I think nearly some 67 people are on live, but please respond. Okay. If you don't understand something, please you can ask me again. I'll come back. No issues. Okay. But make sure that you all understand the things. Ajay, it's all clear? Okay. Okay, Venkat Sai, good. If everything is clear, then I'm happy for you. So now, with this knowledge that we attained, let us try to see what's the volume of a cone, which many of you are telling 1/3 pi r square h. Let us see whether the volume of cone is actually 1/3 pi r square h or it's an approximated formula of 1/3 pi r square h. Okay, so let us go here. Volume of a cone. Volume of a cone. Okay, so now how do you get a cone? Basically by evolving the curve y is equal to mx above x-axis. Let us follow the same analysis again. Let us draw the diagram and all. So if you try to draw the diagram, this is x-axis, this is origin, y and minus y. Now let me okay, let this is the curve y is equal to mx, straight line basically. So if you evolve this straight line, yeah, we'll go for gate questions in next class. I mean Sunday's class. I'll be discussing some 20 to 25 questions, so no issues. So please see here, y is equal to mx is the curve. So now when you evolve this about x-axis, basically how could it look like? I think I'm not drawing fine. So see here. Okay, so now we have cone whose height is h and whose base radius is r. Okay, so see here. So see pi h. Now if this is the case, then this point is nothing but arc h comma r, and this is theta. Okay. Now if you use this expression, what's the equation? Y is equal to mx. So this implies dy by dx is equal to m, basically the slope of this. So if you try to calculate volume of this triangle, volume of this cone, v is equal to, we are interested to find the volume generated of this by this curve when integrating from x is equal to 0 to x is equal to h. So integral 0 to h pi y square, and you know y is equal to mx, so mx whole square into root of 1 plus m square, so 1 plus m square into dx. This is the formulation that we have. Now let us try to calculate this integration. V is equal to, now what are the constants here? Pi is a constant, m is a constant, and root of 1 plus m square is also a constant. So I am bringing all the constants out. Pi m square into root of 1 plus m square into integral 0 to h x square dx. Now this is equal, this implies v is equal to pi into, what is the value of m? Again tan theta, if you consider from this triangle, r by h, so r square by h square into square root of 1 plus r by h whole square into integration of x square dx within the limits 0 to h is h cubed by 3. Correct? Because integration of x square is x cubed by 3. So when you substitute the limits from x is equal to 0 to x is equal to h, you will be having h cubed divided by 3. So let us try to calculate this value. V is equal to pi into r by h whole square into root of 1 plus r by h whole square into h cube by 3. So this is what we had, correct? R square by h square into root of 1 plus r by h whole square into h cube by 3. So see here, if you simplify the things, v is equal to this 3, let me write in the beginning, 1/3 this pi r square divided by h square into, if I take LCM, I'll be having 1 plus r by h whole square. Okay, let me not take LCM for the time being, into h cube by 1. Okay, because we have already taken 3 here. Now if I cancel this h square and this h cube, we have h. So let me write this formula as v is equal to 1/3 pi r square h, writing that h ahead, into square root of 1 plus r by h whole square. This is the actual volume of cone. Okay, v actual. But now in books, why it's given 1/3 pi r square h? Let me tell you. Have you ever gone out to somewhere outside and have you got a cone ice cream anytime? If you see the cone ice cream, the height of the cone ice cream is very big, correct? When compared to the diameter. Yes or no? Similarly, I would like butterscotch. I don't know what you could like, but see here, if you buy an ice cream somewhere, your ice cream could look something like this, correct? Which means basically this diameter is small when compared to this height h in actual practices. Okay, if this diameter is smaller than h in proportion, what about radius? It is still more smaller, and generally this angle, which is called semi-cone angle, will be less than 15 degrees, below tan 15, below 15 degrees. Okay, so if this is the case, if theta is less than 15 in practice, in general applications, then you see this ratio, this radius r is very small when compared to height h. Okay, so which means r by h is small. Of course, it is definitely less than 1, but it will be nearly of the range 0.02 and all these things in practical applications when this theta is less than 15. So if this is the case, then what about r by h whole square? This is very small when compared to this value r by h, correct? And adding such small value, which is of 0.04 something of order, to this 1 doesn't make a big sense, correct? So, or doesn't make a big difference. So that's why, since in school kids like 8th class and 9th class kids, they could go for the formula 1/3 by r square h instead of writing this complete formula, since in practical applications this r by h whole square is very small. Okay, so that's why we approximate the volume of cone to 1/3 pi r square h. Okay, so this is how you see in 8th class books and 9th class books the volume of cone as 1/3 pi r square h, because this ratio r by h in practice is very small. You might have studied this. The semi-cone angle is 12 degrees, 13 degrees, things like this. So tan 15 value is very small, correct? 0.02 somewhere around. So this 0.02 whole square, which is 0.00 and one more 0 into 4, will give you very small value when added to 1. So that's why this term is in general neglected. R by h whole square term is neglected. If you neglect this term r by h whole square, then 1 plus this r by h whole square is again almost equal to 1. So 1 into 1/3 pi r square h is 1/3 pi r square h. Okay. Now many of you are asking me questions. These formulas are when you evolve the curve about the line y is equal to about the x-axis. Now what if you evolve the curves about y-axis? Then you will be having pi x square into dy here basically. If I evolve this curve, which is, let us suppose there is something like this, where the curve is x is equal to some function of y, then if I evolve this curve about y-axis, then this is the distance x at any point, and if you evolve, you will be getting a circle whose things looks like pi x square into dy is the small volume you will be integrating from y1 to y2. Okay, this is how. Into dl, basically dl expression is root of 1 plus dx by dy whole square into dx in this case. So basically this is how you follow this analysis. Okay, now the solids, what I am telling you, cone and all these things are called solids of evolution. Means basically when you evolve a line about any fixed axis, you will be getting this solid. But there are some solids which are not solids of evolution. For example, if you take prism, triangular prism, if you take rectangular prism, all these things. Okay, so these solids are generally not obtained when you evolve a line. So for that we have some triple integration techniques which we deal in tomorrow's class under the chapter multiple integrals. Okay, so no issues. Right now whatever the analysis I am giving only for solids of evolution. Okay, so please take this. Is it clear so far to all of you? Is it clear to all of you? If it's okay, please say yes. All of you who are watching this video right now. Okay, I'm getting a lot of yes. It's fine. Even others, please try to respond if you're online. So basically, this is how you evaluate different solids. I mean, volume of different solids, basically, which are solids of evolution. And a lot of questions have been turned up in GATE examination based on all these concepts. Okay. Okay, I hope it's clear to all of you. So now with this particular point here, we ended up the single variable calculus. Don't worry about practice questions and all. I'll be giving you a lot of things. I'll be uploading links for practice questions, and also we'll be having one doubt session after at required times, so that to clear some doubts that you have while writing the notes and all these things. Okay. So now, sir, you wrote something. Sir, to get a cone, we should rotate a right angle triangle. Yes, actually, the thing I'm doing here is right angle triangle only, because if you see, if you connect this point, the angle between here is 90. Okay. I'll be uploading shortly. Because to show you, basically, root term why I'm not opening is to show you this value is very small in practice. Okay. That's why it is given, it's approximated as 1/3 by R square H. So see here. Next. So with this, we finished single variable calculus, and multivariable calculus, basically two variables and three variable calculus that we deal is of some limited content, which we could finish off hardly by tomorrow, by the end of the second session of tomorrow. So tomorrow, again, I'm repeating, we have 4 hours of class in 2 sessions. So first session is of 2 hours from 7:45 to 9:45, and second session is again from 10:30 to 12:30. Okay, so please be attentive. And now, after the completion of this single variable calculus, now I would like to integrate y is equal to mx is a line, and generally we are rotating a line. Okay, and you will get a cone generally when you evolve a line about any fixed axis. Okay, but the line should be inclined, not a straight line. If it's a straight line, you will get a cylinder. Okay, sir, I hope I am clear. You need not, it's not mandatory that you need to rotate a right angle triangle. If you rotate, you will be getting, but for the solid to be hollow, you can rotate a line. But if you want a solid cone, then you need to rotate evolve a right angle triangle. But here I am discussing hollow things. Okay, this is a hollow cone basically. Okay, so that's why when you rotate a line, you will be getting a hollow cone. But if you rotate a triangle, then you will be getting a solid cone. Okay. So see here. I hope I cleared you on side. We are dealing hollow solids here. Clear? Okay. So now we'll go for two variable calculus, basically multivariable calculus. So is everything clear in single variable calculus to you? Right from the concepts of limits, then following the definition of continuity, then differentiation, then we went for mean value theorems, then we went for Taylor series, and then to the concept of maxima and minima in single variable. Then we stepped into integration. Then we have learned different integration techniques, and we have done whatever the analysis that we have done so far. Okay, so see here. What is the difference between surface and hollow solids? Surface and hollow solid, or solid and hollow solids? See here. Hollow is something which is empty inside. For example, if you take a plastic ball, which many of you have played during your childhood, that plastic ball is a hollow solid, for example, because if you can pin a hole into the ball, you can pour some water into that, correct? Because there is some space inside which is empty. But if you take solid balls, generally, all the solids, like for example, watermelon, if you take, it's a solid. All these things which are filled with matter inside are called solids, and solids basically which are having empty space are called hollow solids. Okay. So see here, yeah, golf ball, lot of things. So see here, multivariable calculus. So till now, whatever we have seen functions like y is equal to f of x. Basically, there is only one independent variable. But in general practice, when we go to 3 dimensions, we can have many independent variables. For example, if you see, there can be some functions like z is equal to some function of x comma y. Here, both x and y are independent variables. For example, if I have a function like z square is equal to x plus y, then the value of z depends upon both x and y, and both x and y can be interchanged as well. Correct? So there can be functions which can deal with multiple variables at the same time. So if you want to write the definition of limits and all again for multivariable calculus, I'm straight away writing the differentiation formulas. If z is equal to z of x comma y, then when there is only one variable, we write differentiation, but when there are multiple variables, we write something called partial differentiation, and partial differentiation is something that we look in now. Then the partial derivative of z, with respect to x, is given by zx. This is how you represent when you are differentiating z with respect to x partially. This is also represented as dou z by dou x at y is equal to constant. Means when you are integrating, when you are differentiating a function which is of multi-variables with respect to a particular variable, apart from that variable at which you are differentiating this function, you treat all other elements as, or all other variables as constants. Means if you are differentiating the function with respect to y, here in this case, you will treat this x as a constant. Similarly, if you differentiate with respect to x like this, you will treat y as a constant. Is equal to, some books they call this as p as well. So p is equal to, all these are same, zx dou z by dou x at y is equal to constant is equal to p is equal to limit h tends to 0 z of x plus h comma y minus z of x comma y divided by h. Means basically we consider change only in the x coordinate when we are differentiating with respect to x. Okay. Similarly, if you want to write partial derivative of y, partial derivative of z with respect to y, then we have dou z by dou y treating x as a constant is equal to q is equal to limit h tends to 0 f of let me write z of, because I have taken the function as z of x comma y plus h minus z of x comma y divided by h. So basically this is how you will find the partial derivatives of two functions when it is involved of a function which is having two independent variables. Okay, so this is the expression for partial derivative of z with respect to x, and this is the definition of partial derivative of z with respect to y. Okay, so let us straight away look at some examples and see how to calculate the partial differentiations. Okay, let z is equal to 3x square y plus 2x y square. Let us suppose this is the function that you have, and let me tell you how to differentiate this function partially with respect to x and partially with respect to y. And I told you, whenever you are differentiating a function partially with respect to x, you will treat all other variables as constants. Correct? So let us keep this point in mind and let us try to calculate zx, which is basically dou z by dou x treating y as constant. If this is the case, now see here, if you differentiate this function with respect to x partially, see, this is the term, first term, dou by dou x of, let me write z here, 3x square y plus 2x y square. Okay, who here is not familiar with this partial differentiation, so I am giving a basic idea, so please see here. So this differentiation you can split at this point, so dou by dou x of 3x square y plus dou by dou x of 2xy square. Now, if you are differentiating the things, when you are differentiating with respect to x, I told you should treat all other variables as constants. So, treating y as a constant, then this 3 and y both are constants which are inside the differentiation. So, I am bringing the 3y outside. 3y into, now, dou by dou x of x square. Differentiation of x square with respect to x is 2x. Plus, similarly, when we are differentiating with respect to x again, this 2y square is a constant. So, writing this 2y square outside. Differentiation of x with respect to x is 1. So, which is 6xy plus 2y square is the derivative of this with respect to x partially. So, this implies this is the expansion for zx. Okay. Similarly, now what's the expansion for zy? Zy is equal to dou z by dou y at x is equal to constant. Correct? So, this is equal to dou by dou y of z. Again, if you write this 3x square y plus 2xy square, this is equal to, again splitting this differentiation at this plus sign, dou by dou y of 3x square y plus dou by dou y of 2x y square. So this is equal to, see, when you are differentiating with respect to y, I told you should treat x as a constant, correct? So if you take this 3x square out as a constant, then differentiation of this y with respect to y is 1 plus dou by dou y of this thing. We are differentiating with respect to y again, so which means you can take this 2x as a constant and bring out this 2x. Then differentiation of this y square with respect to y is 2y. Okay, so basically which is 3x square plus 4xy. Okay, so this is how you will be differentiating the functions partially by treating other variables as constants. Okay, now as we have seen in single variable calculus, we have second derivatives and above order derivatives here. Basically we can, and this is generally denoted by q in many books instead of writing this dou z by dou y. Okay, so see here, yeah, all of you are correct. Whatever the answers you have written here, all of you are correct. So see here, now let me try to show you one thing. If I want to calculate zxy, means which is dou square z by dou x dou y, which is basically the differentiation of dou by dou x of dou z by dou y. If I want to calculate this particular thing, which is generally denoted by s in many books, yes, okay, small s. Okay, so if I want to differentiate this dou by dou x of dou z by dou y, what is dou z by dou y here? 3x square plus 4xy. So 3x square plus 4xy is equal to, now again splitting this differentiation at this plus sign, dou by dou x of 3x square plus dou by dou x of 4xy. So if you see the things now, see carefully, dou by dou x of 3x square, this is only a function of x. With respect to x, if you differentiate, you have 6x plus here dou by dou x of 4xy. Whenever you are differentiating with respect to x, this 4 and y are constants, so this 4y can be written outside into dou by dou x of this x is 1. So 6x plus 4y is zxy. Now I want you to observe one thing, because later the result which I am going to show you now is really important in differential equations. Okay, in differential equations chapter, there is something called exact differential equation, and we'll be getting some conditions. So I want to show you one result now, which is useful actually in differential equations and also in complex variables when we deal the chapter of complex variables. Now what is zyx? Zyx means basically dou square z by dou y dou x. This time we are doing this particular part, dou z by dou x. See here we have integrated the function with respect to y first, and then we integrated with, we have differentiated this function with respect to y first, and then we differentiated with respect to x. But now in this case we are differentiating with respect to x first and then with respect to y next. So if you do this, dou by dou y of, what's the value of dou z by dou x that we got? 6xy plus 2y square. So writing that here, 6xy plus 2y square is equal to dou by dou y of 6xy plus dou by dou y of 2y square is equal to, now treating this x as a constant, because we are differentiating with respect to y, 6x is a constant and differentiation of y with respect to y is 1. Similarly here, if you see, this complete function is only a function of y, so if you differentiate with respect to y, you have 4y, which means this is 6x plus 4y. Correct? And if you see, this is same as the thing on the left hand side, so zyx. So that's why in partial differentiation, order of differentiation is not particular, means dou square z by dou x dou y is same as dou square z by dou y dou x, and this is really one good result that you see in partial differentiations, and this condition is later used in many concepts. For example, to show exactness of a differential equation, then again to validate Cauchy-Riemann equations and all these things in complex variables. We will discuss what are all those equations when we go there. So, but in partial differentiation, as long as the function is differentiable, the order of differentiation doesn't matter a bit. Okay, so dou square z by dou x dou y is same as dou square z by dou y dou x. Means if you differentiate a function with respect to x first and then with respect to y next, or with y first and x next, the answer doesn't change. Okay. Okay. Now I would like to define you something which is called homogeneous function now. Okay, at this point. Homogeneous function. Homogeneous function. A function z is equal to f of x comma y means basically the right hand side is some combination of x and y terms is said to be a homogeneous function. A homogeneous function of degree n if f of kx comma ky is equal to k power n into f of x comma y basically. Okay, this means if your f of x comma y means basically your z is satisfying this condition, then you say this f of x comma y, which is basically this z, is a homogeneous function of degree n. Okay, basically for example, if you see the example that we discussed here, 3x square y plus 2xy square. Let us consider the same example. Example, z is equal to 3x square y plus 2xy square plus 2xy square. Okay, if this is the case, now see here, z of kx comma ky, something is happening here, type kx comma ky is equal to 3 into, now instead of x you should put kx, correct? So kx whole square into ky plus 2 times kx into ky. Something is happening, this sensor is giving some issues. Okay, so 2 into kx into ky whole square. Okay, so this implies z of kx comma ky is equal to, now see carefully, here there is one k square, here there is one k square, and there is a multiplication of k, which means I can take k cube out of this polynomial. So k cube into 3x square y plus, again here there is k cube, so if I take k cube common, I'll be having 2xy square. Means basically if you take k cube common from all these things, you have 3x square y plus 2xy square. Yes or no? 2xy square. So this implies z of kx comma ky is equal to k cube into, if you see this expression is same as z of x comma y. So z of x comma y. So which means you say here this z is a homogeneous function of degree 3. Therefore, z is a homogeneous function of degree 3. Okay, so basically you call this functions as homogeneous if this particular condition is getting satisfied, and this function, as we discussed, this z is a homogeneous function of degree 3. Correct? Now I want you to calculate some result for this function. If z is equal to 3x square y plus 2xy square, then the value of x into dou z by dou x plus y into dou z by dou y is equal to dash. This is a thing that I want you to evaluate now. Okay, please evaluate this and tell me the answer. What's the answer for this? 3 wrong. 3 is a wrong answer. Rahul, please check. I am giving you some time to solve this. Please solve and tell me the answer. See, you have these values of expressions, dou z by dou x and dou z by dou y, which we already calculated here in this part. Correct? We found what is dou z, what is dou y. Then you can put 2z, wrong answer, Monica. 3z. Sarath, it's correct. Nagasarath, you are correct. The answer is 3z. Okay. So let us see the things. 3z is the correct answer actually. So see here. Solution. If you try to solve this now, 3z. Yeah, all of you are correct. The answer is 3z. So if you try to evaluate this expression, we have zx. Basically, dou z by dou x is equal to, what's the value of dou z by dou x? 6xy plus 2y square. Correct? Similarly, what is zy? Which is dou z by dou y. With respect to y, when you differentiate, 3x square plus 4xy. Correct? So now see here, if you substitute these terms here, therefore, x into dou z by dou x plus y into dou z by dou y is equal to x into this particular part, which I have written here, 6xy plus 2y square plus y into 3x square plus 4xy. So now if you multiply the things, 6 into x into 6xy is 6x square y plus, here if you multiply this y, you have one more 3x square y. Similarly, this 2 into xy square will give you 2xy square plus 4xy square, which means if you take the terms here, we have 9x square y plus 3 plus 2 plus 4 is again 6xy square, which means if you take a 3 common, you have 3x square y plus 2xy square, which is nothing but z, 3 times of z. Therefore, x into dou z by dou x plus y into dou z by dou y is equal to 3 times of z. This is what we achieved, correct? But without doing all this calculation, there is one person called Euler who gave some theorem for this, and it's called Euler's theorem. Okay, now let us see what is that Euler's theorem in partial differentiation. Euler's theorem. I think some of you might pronounce it as Euler's, whatever you can. Euler's theorem or Euler's theorem in partial differentiation. Okay, so let us see what are the points here. What he told: if z is equal to f of x comma y is a homogeneous function, of degree n, then first point is x into dou z by dou x plus y into dou z by dou y is equal to n times of this z. Okay. Second point, what he told is x square into dou square z by dou x square plus 2xy into dou square z by dou x dou y or dou y dou x, doesn't matter the order of differentiation, plus y square into dou square z by dou y square is equal to n into n minus 1 into z. This is what he has given as Euler's theorem for this function. Basically, z is equal to f of y if the function is homogeneous. Now, if you see this preceding example which we discussed, you know that this is a function of degree 3, because we have seen here this function is a third degree homogeneous function. So as per this Euler's theorem, now if I ask you this value, and you know if this function is a homogeneous function of third degree, you can straight away tell here the answer is 3z, which we evolved after doing all this procedure. Okay, so this is how Euler's theorem is defined in partial differentiation. So please look at this. Okay, take this, all these things. If I'm going a bit fast, because I know these are very simple inceptional topics which many of you might be familiar, so I'm going directly with all these things. Okay. Am I audible to all of you? Please say yes if I'm audible. Okay, so fine. Okay, so I hope all of you are getting the things now. So basically, this is what Euler's theorem is given for. Okay, and generally there is some nomenclature for these partial derivatives. This is denoted by P. Then Q is dou z by dou y. R is equal to dou square z by dou x square. S is dou square z by dou x dou y or dou y dou x, and T is given by dou square z by dou y square. Okay, so these are generally denoted by P, Q, R, S, T. Homogeneous function basically means all the terms in that function are of same degree. For example, if you see here, the degree of this particular term 3x square y is 3 because there is 1 here. Similarly, there is 2x y dash, 2x y square, degree of x is 1 and degree of y is 2. So which means homogeneous function basically tells that all the terms involved in it are of same degree. Okay, I'll erase this dash because some of you may feel this is a derivative again. So these are the things as of now. Okay, so basically this is homogeneous function. Now with the help of these things, see, now you got to know how to calculate partial derivatives. Okay, so and if I give you a point x naught y naught, you know how to substitute at this points. For example, if I ask you what's the value of zy, for example here zy at the point 2 comma 3, then you should substitute this point 2 comma 3 in this expansion basically at the place where x is equal to 2 and y is equal to 3, and tell me the numerical values of this derivatives. Correct? So let me introduce you one important concept here at this stage. Since you know how to calculate partial derivatives of z with respect to x and y, and also higher order derivatives means dou square z by dou x square, dou square z by dou x dou y, and dou square z by dou y square. Since at this moment you know how to calculate all this, I would like to go for the concept of maxima and minima in two variables. Okay, concept of maxima and minima, in two variables. See, as of in one single variable calculus, when I discussed the concept of maxima and minima, I have given you graphs and variation of slopes at every instant. But right now, this is not possible on this two-dimensional board because drawing 3D and plotting all the things is very difficult at this moment. Okay, so I'm straight away giving you the procedure how to calculate the maxima and minima when you are given a function of two variables or maybe more than that. Okay, so initially we'll discuss for two variables, then we'll see what are the other cases when there is three variables and other cases. Okay, so here I'm not dealing with geometrical things again because drawing three-dimensional things and explaining will take a lot of time, and it's also of not necessary for GATE examination by using all these curves. So I'm giving the procedure to find. I think still we have some time. Yeah, 10 minutes of time, so we could deal. Procedure to find the extremum. In the sense of extremum, I mean either maximum or minimum, doesn't matter. Minimum for the function z is equal to z of x comma y, or basically if you are confused you can write f of x comma y as well, doesn't matter. This just represents this is a function of x comma y things. Okay, so z of x, f of x comma y. So see here, if you are given a function like this, z is equal to f of x comma y, then we need to find maxima and minima for this function. Then what's the standard procedure that is with us? Let us follow now and let us calculate the things. Steps. First point, calculate P is equal to dou z by dou x and Q which is equal to dou z by dou y, and equate P is equal to 0 and Q is equal to 0. See, in single variable calculus, you differentiated the function with respect to x and you equate it to 0. But here, since there are two variables, you will find partial derivatives dou z by dou x and then dou z by dou y, and then you will equate both the things to zeros. Okay, so basically equating P to 0 and also Q to 0. Then next, Find stationary points. Find stationary points and let x0, y0 be one stationary point. Be a stationary point. See here, basically the function is of two variables, correct? Z is equal to f of x comma y. So when the function is of two variables, then when you find dou z by dou x and dou z by dou y, then you will be getting two functions. Means basically p, if z is a function of x comma y, then p can also be a function of x comma y, and similarly q can also be a function of x comma y. So if you equate those two things to zeros, then you have two variables x and y and two equations to solve them, correct? And again, number of stationary points quietly depends upon what's the degree of this z. Okay, and let us suppose x0, y0 be one such stationary point. Okay, clear so far? Basically we are differentiating this function with respect to x and y and then equating the terms to 0. So now you will be getting two equations in two unknowns. So if you solve them, you will be getting some stationary points where these derivatives are zeros, and I am doing the analysis by considering one such stationary point. Okay, so see here, 3, calculate RT minus S square, where R is equal to dou square z by dou x square at x0, y0. S is equal to dou square z by dou x, dou y, or dou y, dou x at again x0, y0. And what about T? Dou square z by dou y square at x0, y0. Okay, so basically you are calculating this value RT minus S square, where R is the second derivative, S is this second order derivative, and T is also second order derivative with respect to different variables at this stationary point that you obtained. Okay, next. Now we have different cases. See, this is common till here for single variable calculus and multivariable calculus, equating to the differentiation to 0, then finding stationary points. Then there you will calculate second derivative f dash double dash of x, but here you are calculating the value of some expression where Rst is given by these three values, correct? So going for next thing. Case 1. If RT minus S square is greater than 0 and R is also greater than 0, means basically when you evaluated these values, this value should be positive, and also this complete value RT minus S square should also be positive. In that case, if RT minus S square is greater than 0 and if R is also greater than 0, then the function z is equal to f of x comma y has minimum at x0, y0. And what about the minimum value? And the minimum value is f of x0, y0, which is basically z minimum. Okay, now case 2. Okay, case 2. If RT minus S square is greater than 0 and R is less than 0, means basically when you calculate these values, this value is negative but this total value is positive, then the function z is equal to f of x comma y has maximum at x0, y0 and the maximum value is, yes Vinay, this class is daily, maximum value is z of maximum is equal to f of x0, y0. Case 3. Case 3. If RT minus S square is equal to 0, then we do not have maximum. Okay, you can write one more thing here, less than or equal to 0. Okay, so because for less than also same situation holds good. So if RT minus S square is less than or equal to 0, then we do not have maximum or minimum at such points, and those points are called what do you say? Saddle points. Okay, yeah, saddle point. What Nags have told you're correct. So basically, this is how you'll check whether a function has a maximum or minimum at a given point, at a given stationary point. So this is the procedure how we are going to work out the things. Basically, I'm repeating. You'll calculate the first order derivatives, dou z by dou x and dou z by dou y. Then you'll equate the two things to 0. Both p is equal to 0 and q is equal to 0. Then you'll be getting some stationary points, and let us examine each stationary point. So calculate these three values r, s, t, basically the second order derivatives of this z with respect to x, with respect to both x and y, and then with respect to y alone. Then you'll be getting this r, s, t values. Now check for these conditions. Definitely it should satisfy one of these conditions, and definitely it should satisfy one of these conditions. So obtaining the condition that is at that moment, you can decide whether the function has maximum or minimum at that particular point. Okay, and you can also get the maximum and minimum values for this function. So it's a 9-12 before going for the next thing that we can discuss today. So there's okay. So I hope now it's audible to you. Now it's audible? Okay. So see here. So basically we have discussed the concept of partial differentiations, and we have seen Euler's theorem, and we have seen how to find maximum or minimum for a two-variable function. And in tomorrow's class, basically we finish this basic calculus after dealing the concept of multiple integration, and for Monday we'll be starting differential equations. Okay, and this basic calculus is really important for us in applications of engineering as well, because we need to find maximum. Again, no audio. Is it fine, Subramaniam? Is the audio clear to all of you? Okay. So see here. So this is what we have seen. Coming to practice problems and all, again I will be uploading some documents so that you can have a lot of practice problems with you. And I suggest you one important thing at this moment. Whenever you are trying to get numerical values, for example 2 into 2 minus 1, all such things, please start using virtual calculators. Okay, don't use this Casio punching keys and telling the answers at first. Okay, because in final exam you're not going to use Casio, you're going to use only Gate virtual calculator. Okay, and that calculator really makes a big difference in calculations, and many of you will be sitting idle at the point of calculations in exam. Please don't do that. So please start practicing virtual calculator. If you need any help, we'll be providing our contacts shortly so that you could access us for doubts and all these things. Regarding documents, I'll upload the links again. You can very soon, so that you can have a lot of practice problems. And if the link is not working, please install Telegram app, okay? Because if you click the link, that will direct you to Telegram app for the installation. If you don't have the Telegram app, you won't be able to open these links and all, okay? So please install Telegram app. And yeah, Vinay, this class is going daily. Gate classes we are continuing daily, and soon we are opening a course of thermodynamics as well for gate classes. I'll be dealing that course of thermodynamics as well very soon. So all the mechanical students who are interested, you can come for that as well. We'll be revealing when the course is getting started very soon, probably in tomorrow or Monday's class. Okay. So I hope things are clear here. So it's 9:15. Yesterday's notes we have already uploaded there. You can check that here. Psych and what about electrical students? You better talk to management people and all. So that's from my side for today's class. If you have any doubts, you can talk to me, or else it's fine. And I'm repeating, tomorrow's class is from 7:45 to 9:45 as first session, and 10:30 to 12:30 as second session. And in tomorrow's class, we'll finish off this basic calculus. Okay. Okay. So any issues so far? Is everything going fine? Okay. So if things are going fine, I request you to like the video, and you can write it in the comment box if there is something that we can do better. Okay. So then thank you all. That's from my side for today. Signing off. Bye. Have a nice day.